What are the internet performance parameters? They're defined as metrics that are used to evaluate and to optimize the quality and the reliability of an internet connection. There may be many of them defined, and some of them are listed here, such as transmission speed, transmission time, propagation time, channel crossing time, packet loss, and queuing delay. Transmission speed is defined as the rate at which the digital information is transmitted over a communication channel. Transmission speed is measured in bits per second, or its multiples such as kilobit per second, megabit per second, or gigabit per second. The transmission time, which it takes to transmit L bits, depends on the transmission speed, R, which is expressed in bits per second. The propagation time, in turn, is defined as the time tau for a pulse or a bit to be transmitted from the transmitter to the receiver. This propagation time depends on the distance expressed in meters or kilometers and the propagation time v, which is expressed in meters per second. In this case, we see a simple example of transmitting a series of bits from a transmitter to the receiver in a distance d, given a time, which in this case, as we have defined, is given as propagation delay tau. The channel crossing time, in turn, is defined as the time or the delay between the transmission of the first bit and the reception of the last bit. For example, the total time, which we have expressed here as t dot, which represents the channel crossing time, is the sum of the time which it takes to transmit all the bits and the tau, or the propagation delay, to transmit the bits from the transmitter to the receiver. Here we provide an example between a transmitter and a receiver. We provide the time t0 in which we start the transmission. The transmission which parts from the tx starts with the first bit and continues up to the last bit. Time t1 is defined as the time in which the first bit arrives on the receiver Rx. Time t2 is defined as the time which we need to end the transmission or to transmit the last bit. Instead, time t3 is the time which we need to receive the last bit on the receiver side. Given these parameters t0, t1, t2, and t3, we can calculate both the transmission time and the propagation delay, all of them with their particular measurement units. This is another example in which we again transmit from the transmitter tx to the transmitter to the receiver Rx. At t0 we start the transmission. The difference here is that the time t2, where the transmission ends, is smaller than time t1, which is needed for the receiver to receive the first bit. And time t3 is the same as in previous example, in which the last bit has arrived. Also in this case, we can use these parameters to calculate the transmission time, the propagation delay, with their corresponding units. What about the case where there are more equipment in the network? In this case, we have 3 routers, A, B, and C. For each of them, we define the transmission time in each of the routers. We start from the router A. The time defined as TAB is the time that it takes to transmit this message from the point of view of router A. Then we have tau AB, which is the propagation delay to transmit the information from router A to router B. Then such information gets received at router B, and router B proceeds and transmits it to router C in the same way. Also here we define that we have TBC, which is the time taken by router B to transmit this message, and tau BC, which is the propagation delay which is needed to transmit this information or to propagate this information in the link between B and C. Then we have another example, again connecting routers A, B, and C. In this case, we notice that the time that it takes to transmit this information might vary. And to understand why this example provides, let's say, a shorter time compared to the previous one, we need to go and understand a bit better what happens also inside a network node. In fact, the incoming packets which come to a router or any network nodes, depending on the destination where they need to be transmitted, may vary, because each node first waits for packet processing, and then once it does the processing of the packets, it continues with the selection of the interface, and then it proceeds with the transmission of the interface of the packet in the corresponding interface. In fact, in each of the interfaces, it's possible to have a queue depending on the quantity of the data to be transmitted and depending on the processing capacities of the node. In case such queues are full because they have limited size, then what happens is that packets might be lost. In fact, here we see an example in which 2 packets have to be dropped because the queue is full. And the decision on whether these discarded packets, lost packets, should be retransmitted or not depends actually on the protocol that manages the loss of the messages. From a point of view of the nodes, we also have to take into account the processing time, which is defined as the time that each of the nodes needs to process the message that it receives. In this case, we see that transmitting a message from point A to point B requires a transmission time TAB. There's a propagation delay, as we have defined before, tau AB, and there should be also processing time at the node B. However, in today's devices, the assumption is usually to consider that such processing time at the nodes can also be negligible. That's why we define that PB is approximated to 0. Then we provide an example. Here we have a queuing delay. We have again 3 nodes A, B, and C. Transmitted information which is transmitted on link 1 and link 2. We have 2 packets that need to be transmitted. The transmission time of packet 1 is T1A, which requires a transmission propagation delay equal to tau 1. However, we notice that since the capacity of the link 2 is supposed to be lower than the capacity of link 1, it may be that by the time that packet B arrives at node B for retransmission or for being further forwarded to node C, then it has to wait because node B is still transmitting the first message or is still transmitting packet A. What about cases in which messages have to be sent in different interfaces and in different equipment? Here we have an example of 4 nodes, A, B, C, and D. We have packet A, which is destined towards C, and packet B, which is destined toward D. In this case, we notice that once packet C has been transmitted from A to B, since packet C and packet D have different destinations, B can proceed with the transmission of packet A, and at the same time, B can proceed with the transmission towards node D.